everybody. We are already quite behind schedule. So without further ado, let's start today's lecture. So some of you might know me. I am Akshank. I am a 5th year physics major, so a senior for most of you. And I am currently working at CHEP, and previously I also worked at RRI in CMD Cosmology. So I hope you'll be able to learn a few things. So I'll not be teaching you much about the mathematics of cosmology, but more about observational cosmology and what it actually means when we talk about the universe, what are we actually talking about, and what are the phenomena that are happening inside this universe of ours. This should also be a video. Yeah. I forgot to play the video, but it's a nice fly through galaxies, let's say. Some of the topics that we'll cover: first we'll talk about the cosmological principle, without which any kind of cosmology is really hard to do. Then we go on to explain what is the cosmological redshift and how the universe is expanding. Then we talk about the shape of the universe. We also talk about how telescopes can be used as a time machine, and if we get time, we'll talk about the Friedmann equations today. So we start off with a very general question: what is the universe? For you, what is the universe? Any answers? What do you think? I don't want you guys to be sitting quietly. I want you guys to answer. So, what do you think? Let's keep it simple. For an early person, for an early man, an early human being, what do you think the universe was? Earth, right? The globe. It had nothing else apart from the land he lived on. So that was his entire universe. But we grew up. The human civilization grew. And then we thought, we looked around in the sky and we were able to pinpoint planets, right? Those planets then gave us the solar system. So this is a medieval universe, you can say, medieval cosmology, how people thought about it. So this is a geocentric universe. The Earth is at the center, and then you have the Moon, Mercury, Venus, and then the Sun, which is also, according to them, going around the Earth, right? And obviously we know this is wrong, but this is how you would think actually. If you were also living in these primeval times, you would have also thought of something similar, because the sun seemed to move around the Earth, so it was easier to explain that the sun was moving around the Earth. Okay. Next, people started looking more deeply. They were able to look at individual stars. They were able to look at the band of stars, which is called the Milky Way galaxy. Has anybody seen the Milky Way in the sky? It is, I know, it is very difficult to see it in today's light pollutions, but hopefully in the future, some of you will go to, let's say, a hill station or somewhere. So try to look at it. It does not look, unless you are at Ladakh, you don't really get pictures like this. But still, you might be able to see a fuzzy cloud near the Sagittarius constellation, and that is basically your Milky Way. But earlier, when there was much less light during the night times, you could very clearly see the band of the Milky Way. And so people progressively thought that Milky Way must be the entire universe, right? First we were limited to the Earth, then we went on to the solar system, now we are at a galaxy scale. So we think that Milky Way must be the entire universe. And up till 1920, okay, even beyond 1920, people thought that Milky Way was the only galaxy in the universe, and that was the entire universe. Everything that can be found was in this galaxy. But were they correct? Yes or no? No, they were not. So there is a very interesting debate between Shapley and, which is called the Great Debate of 1920, between Shapley and Curtis. So they argued, is Andromeda a separate galaxy, or is it a part of the Milky Way? No surprises there. We already know it is a new galaxy. It's a different galaxy, and so the universe was actually much larger than people thought. And this is one of our current understandings of the universe. So this is the entire observable universe. We'll come back to what is the observable universe later, But for right now, you can see it's a logarithmic interpretation. So you have the sun, the solar system, around which we have the stars. You can't see the names of the stars and stuff, but it is there. They are labeled very well in this image. You have all the stars in the Perseus arm of the galaxy, Milky Way, and then you have the nearby galaxies. Then you have Andromeda, the other galaxies that we see, and then we see as we go look farther and farther, we start to see nothing. Right? What is beyond here? We'll try to answer that hopefully by the end of today's lecture. Okay. So just a brief overview. What is cosmology? It basically deals with the nature of the entire universe. It deals with questions: where did the universe come from? What does the universe actually look like? And how will it evolve in the future? Those kinds of questions. And some of you or most of you would know what is our current best understanding for the origin of the universe. Do you know? What is it called? The Big Bang model, right? Oh, sorry, wrong one. This one. The Big Bang model, right? We believe that the universe was a very tiny, hot place, and it expanded rapidly to give rise to everything that we see today. That's fine. So what actually is the Big Bang model? As I said, it started from an initial state which was infinitely dense, infinitely hot, and all the particles, all the mass, and all the energy of the universe came from that point. Not all the energy, I'll take that back. But yeah, so these are the few things you need to require if you want to actually study the Big Bang model, and we'll study them one by one. Okay. So the first most important thing, the cosmological principle. It is the basic fundamental assumption, let's say. Keep in mind, it's still an assumption that the universe at large scales is homogeneous and isotropic. What does homogeneous and isotropic mean?
Uniform.
Yeah, homogeneous means uniform. Isotropic?
Uniform.
Very good. Homogeneous is uniform in translation. So if you are at one place, the universe behaves the same. If I move, the universe behaves the same. Okay? So it also means that the universe around me looks the same. It also talks about physical laws. So homogeneity means that gravitation, which we observe here on Earth, will be the same everywhere in the universe. So the gravitational constant, capital G, will be the same everywhere in the universe. Where does this come from? The assumption of homogeneity. Okay? And then you have isotropic, which means if I look above me, the laws of the universe will be the same. If I look below, the laws and the observables will be the same. Okay? Good. But are they both independent of each other, or do they happen together always? Any idea? The answer is no. You can have universes which are homogeneous without being isotropic. So you have this universe where you can see there is a special direction. There is some kind of vector field which is always pointing to the top. So that has a special direction, right? So that is not isotropic. If I look below me, there will be a different, this force field or whatever, this vector field will be different in different directions, right? So there is an inherent direction in this universe. So this is not isotropic, but it is homogeneous. The direction is same everywhere. Similarly here, we have an isotropic universe. If you are at the center of the sphere, in all directions you will see the same universe. But it is not homogeneous. The particle densities are different at different places. Yeah.
You told that over large scale we assume homogeneity.
Yeah.
So what do we mean by large scales?
Very good. So is this room homogeneous? No. I am standing here, right? And then there is a gap, and then you guys are sitting. So it's not homogeneous. There is air in between. It's not homogeneous. Similarly, when you look at galaxy, a galaxy is also not a homogeneous system. It has multiple stars, which are randomly aligned. Then you have two galaxies, Milky Way and Andromeda. So you see, I will not see Andromeda in all the directions, right? I will see Andromeda only in particular direction. But now if I look at scales much larger than this. So let's say, have I that slide? Let's come to that. Next slide. How do you test these principles? So this is the scale of all, this is an image of all the galaxies that we have mapped out in the universe. This is something called the SDSS survey, Sloan Digital Sky Survey, which has all the galaxies up to very large distances. Okay? Now what you see is, you see this cosmic web kind of thing, right? This is a web. Here you will see much more galaxies, somewhere you will see less galaxies, right? So at these scales, there is inhomogeneity. But if I integrate over all of this distance, or I go very far distance, then it basically means that the number of galaxies seem to be homogeneous. Okay? So the density of galaxies at, let's say, a megaparsec scale or 100 megaparsec scale, which is a big scale. At that scales, the density of galaxies become constant. So that is what homogeneity is, and it's actually observed. So from this data, if I try to plot how many galaxies are being observed at what magnitude, so how bright these galaxies are. So it's like a cumulative plot, number of galaxies and their brightness, you can assume. So you see, it becomes a constant value. It has a constant slope, right? So this actually, the gray line that you have, that represents a homogeneous density. And so you see the number of galaxies actually follow this. Here you actually have stars. These are the stars inside Milky Way. And you see, because a Milky Way is plane, it's not 3D, so they will have a different slope. They are also almost homogeneously distributed inside the galaxy, you can say. But because it's in a plane, they will have a different slope. And galaxies will have something different. Okay. So homogeneity is proven. How? By these galaxy surveys. Then isotropy. Any idea for how we can observe isotropy in the universe? Nothing? Okay. So one of the earliest proofs of isotropy was something called the cosmic microwave background, CMB. So this is the light coming from the earliest time of the universe, just 300,000 years after the Big Bang. Okay? We'll talk much more about it in the later lectures if we have them. So what you see, again, this is a radio observation, microwaves. This was done in 1965, I believe. I might be wrong. Don't take my word on dates, I'm bad at those. But you see that there was a uniform temperature of 2.785, right? 2.725 Kelvin. And this was observed all over the sky, in all directions, uniformly. And this was the best black body we had ever observed. Okay? All the directions had temperatures at 2.725 Kelvin. Similarly, if we look at other radio sources, so this is a list of 31,000 bright radio sources. They also seem to be isotropically distributed. So we are here, and this is in RA. So basically longitude around us, and we see same number of galaxies or same number of distribution for these radio sources in all directions around us. So that's good. But again, I will remind you that isotropy and homogeneity is an assumption, and only at large scales. When you start looking much more deeply into anything, you actually see that isotropy or homogeneity both break down. So when we look at CMB in more detail, you see it's actually not isotropic. At different points, it is somewhere colder, which is the blue region. At some points, it is slightly hotter, which is the red region. We'll talk much more about it later, but that's it for now. But this delta, which is basically the deviation that is happening in cold and hot, is actually quite small when compared to this 2.725 Kelvin mean temperature. So it's still we can still make a good assumption that the universe is isotropic. Okay, the deviations are actually quite small, and they happen only on very small scales. Okay, good. Any questions? Homogeneity, isotropy done? Yeah.
If we have experimentally observed the homogeneity and isotropy,
Yeah.
then why are we saying that it's just an assumption?
So the main thing about it is we have observed, again as I said, we have observed it in some things, right? In these objects, in these in this CMB line, right? But there's also a term of being statistical, something called as statistical homogeneity and statistical isotropy, which are still debated. We know that the universe is isotropic and homogeneous, but if it is statistically homogeneous or isotropic, it's still debated. What it means is, has this come from a Gaussian random distribution of possible universes? Something like that. Okay? If that might not be true, that is still something that people work on.
Okay, so there is probability that we may be wrong.
Yes. So I currently work on statistical isotropy in CMB. So we actually have observed problems in the CMB maps that we see. There seem to be a specific direction, and we are trying to understand if that direction or if that anomaly means that we are wrong about isotropy, or does it come from some kind of systematic. Okay? Then our physics is right. We just made a problem in the instrument. Okay, good. Next, we move on to a very simple topic, redshift. I am guessing most of you have heard about Doppler shift, right? You have studied it in sound waves. You might have also seen it in light rays, right? Electromagnetic rays. What it means is, if a source is coming towards you, light will be blue shifted or red shifted? Blue shifted. If it is going away, it will be
Red shift.
red shift. Good. And these are the formulas. Most of you already know this. This is a slight joke I like to make. Roses are red, roses are blue, depending on their relative velocity to you. Right? But why am I telling you about redshift in a cosmology lecture? So let's take an example. What this redshift actually looks like. So here you see that these are the spectra of some objects. Okay? And these are the spectral lines inside the orange circle. And you see, depending on where it is redshifted to, so you have wavelength in the x direction, and you observe that these spectral lines are moving. And based on this, you can tell how fast this object is moving, right? And all of them are redshifted, which means they are moving away from us, right? What these objects are basically galaxies. What we have observed are that most of the galaxies in the universe are redshifted. All of them are moving away from us, right? And that's a puzzle. That's a huge puzzle. How can you explain that?
What is these numbers?
Huh?
These numbers.
These numbers or these ones?
These, second.
These ones? These are the velocities. So, remember this formula? Here you have the redshift directly proportional to d by c. So, from here you can directly calculate what is the velocity, right? If you know the redshift. So, if you have the redshift, you know the spectra, from there you calculate redshift, from there you calculate velocity. Yes?
How do you know how much it is redshifted? Like, you know what light you are receiving?
Yes.
How do you calculate what light you should be receiving?
No. So that is where the astrophysics comes in. What we are measuring is the redshift in these spectral lines. Okay, so these are absorption lines. Let's say this is for a particular element, sodium. You know in a rest frame what wavelength light is absorbed by sodium or is emitted by sodium, right? So you expect them to be visible at the same wavelength everywhere in the universe, right? So these are, let's say, the sodium lines, and I observe them at a different wavelength. So just do lambda by lambda observed by lambda emitted, and you get what is the redshift. Okay? From that redshift, you can calculate the velocity, how fast it is moving away from us.
These elements whose lines, spectral lines we are saying, they can be predicted using the mass of the stars?
No.
Predicted mass of the stars.
No.
Then how do you know what elements lines?
Very good. So that actually depends on the spectra itself. How deep that spectra is, that gives you how much that element is abundant, and particularly it's basically a modeling. So you know that all of these spectral lines are visible, right? And then by imaging their distances between them. Okay, so you have, let's say, 2 sodium lines, then an oxygen line, then a carbon line. You know all 4 of them will be visible in this small wavelength region. And then you try and find, are they same 4 values appearing here, are they not appearing here, right? And then you basically compare. So you just compare this standard spectra that you have with the observed spectra, and you try and match. Okay? It's just a multiplication. Redshift is just a number, a very important number. Okay. So as I was saying, these are the velocities at which the galaxies are moving away from us, and what Hubble in the year 1929 observed that how far the galaxy was, faster it was moving away from us. Okay? So these are the distances. Don't worry about the units, don't worry about what this small h is. You have to see, this is a nearby galaxy, it is moving slow. It is a farther galaxy, moving faster, even far, moving faster again, so and so. So if you go look at galaxies which are farther away from you, all of these are moving faster. Okay? Now this is again a huge conundrum as how that is possible, but this was nonetheless observed by Hubble. Okay? So this is what Hubble had observed in 1929, and he saw there is a direct correlation between the velocity and the distance to these galaxies. And he gave law, very famous Hubble law. Okay? I like to call it the Hubble-Lemaitre law, because Lemaitre also did contribute to this. What it means is the recession velocity, or the velocity of a galaxy moving away from us, is dependent on the distance. Okay? This distance to the galaxy. And then there is a constant, x naught. This is called the Hubble constant. It is a very important number in cosmology, and it's a hugely debated number. So people assume it can have values 67 to 70 kilometers per second per megaparsec. What it means, if 2 galaxies are 1 megaparsec away, they will be moving at speeds 67 kilometers per second. Okay? So these speeds were observed. So what you are observing is something like this.
What was that VP?
Huh?
What was that?
VP. Okay, good. So this is the peculiar velocity, which is basically that not only are the galaxies moving away from you, some are also moving in other directions. Okay, that is the random motion of the galaxies. So you see that not actually all of them are not actually lying on this line, right? How do you explain that? So not all the galaxies are just moving away from you because of this expansion, or because of this movement. There is also some other peculiar velocity which is causing them to move in other directions. That's why that was explained. But when we look at much larger scales, these peculiar velocities become less and less. Okay? So this is the Hubble's data is only this much, very very small, a few megaparsecs even. Okay? But today's data, which is based on supernova, is actually much larger, and you see a much better fit. So there peculiar velocity is not important. There you get a better fit for VR equals to h naught v. Okay. So what you are observing, that there are galaxies in all the direction around us, and they are moving away from us, right? And a galaxy's velocity, recession velocity, is dependent on the distance. So if the galaxies are farther away from us, they are moving faster. But how do you actually explain this? So I have a very nice simulation about it. Okay, so yeah, this is fine. But this means that all the galaxies are moving away from the Milky Way. This is what we observed, right? But in the start only we discussed about homogeneity and isotropy. This is neither homogeneous, it is isotropic, yes, but it is not homogeneous, right? What it means? Galaxies here are moving away faster. Why is that possible? Where we are not even moving at all. So I told you, right, that this galaxy here is actually, it seems to be moving very, very fast, right? Other galaxies are not moving this fast. How is that possible? And how does that actually look like? So I have a good simulation for that. Let's see. Give me a second. Okay. So this is a very nice. It's just a very simple simulation. It shows we are here, and these are all the galaxies that you can observe, and they are moving away from us. But now, if I impose homogeneity, it means galaxies are moving away from this galaxy also. So if I look from this galaxy's perspective, then all the galaxies are moving away from this galaxy also, right? If I look at some other galaxy, the galaxies are moving away from here as well. Yeah. Whenever I click on a new galaxy, you see farther galaxies are moving faster, right? But how do you explain such a thing? How do you explain such a phenomena? And there is a very simple and intuitive explanation that comes from, which is basically expansion of the universe itself, expansion of the space between objects. So you look at these two galaxies, and this is your universe. The universe is expanding. The space between these two galaxies is increasing. The position of these galaxies is not changing. We look at this position related to this grid point. The galaxy stays at the same grid point. What is happening is the grid itself is becoming larger, right? The sphere on which it is located is itself getting bigger. And this is the expansion of space. So first we observed cosmological redshift. We saw all the galaxies were moving away from us. How is that explained? That is explained by using this expansion of space. So galaxies are actually not moving at all. Got it? Whenever you hear expansion of space, whenever you hear cosmological redshift, galaxies are not moving. They are stationary, except for the peculiar velocity. In that case, they are moving a little bit in random directions. But because of this expansion, they are always moving away from each other. Right?
Okay, so what we are saying is that the coordinates are fixed, the unit is changing.
Not the unit, but the scale of the unit.
That
Yeah, something like that. So the unit actually remains the same, but the scale itself becomes larger. So let's take an example of a ruler. Right? We have a 6-inch ruler. Right? Basically, I'm adding a little bit extra on the sides. So what is happening? This ruler itself became longer. The definition of the inch remains the same. So now the ruler became 7 inches. Something like that. So this unit actually remains the same. The definition of the unit does not change. 1 megaparsec is the same. Okay? What is happening?
No, but basically what we are saying that the
Yeah.
distance between the grid points. Suppose I take some random point as
Yes.
origin, the distance is changing, right?
Yes.
But its location in space is not changing with
Yes.
respect to that point.
Yes, yes.
So that location is determined by the coordinates, right?
Coordinates, yes.
The coordinates are not changing.
The coordinates are not changing. The coordinates are just the distance between the coordinates is increasing. Okay. But so you cannot actually say it's the unit. When I write it here, this. So let's say this is your grid, right? 0, 1, 2. Okay. Take whatever. A unit is 4. Okay. Now, so here this 1 unit is equals to 1 foot. Now if I expand it, what happens? The grid itself became larger. Right? Coordinates remain the same, 0, 1, 2, but the definition of feet is still the same. Okay? So the distance between the coordinates grew. The length scale of the coordinate system grew. The unit is the same. Okay? Because that is independent of this expansion. Okay, good. But again, so I said that galaxies are not actually moving away, right? Then why is the light redshifted? If the galaxies are stationary, why is the light redshifted? Yes?
Because the distance is increasing, right?
Yes. So?
So it's traveling more distance between the galaxies, like relative to one galaxy, there, like the galaxy is moving towards, like away from the source, observing point place.
Relative, yes. It seems like it is moving away from you, right? But as I said, it seems it's actually not moving, and Doppler shift actually requires some kind of movement. Why is it redshifted? Yes.
Is it like the space is expanding, so the light wave is some kind of stretching?
Very good. So, when the universe is expanding, the wavelength of the light is also expanding with it. Okay? It is very fundamental and interesting concept. What actually this redshift is that the wavelength itself. So, you had one wavelength of light. Okay, what happened? Let's try another marker. Okay. So you had one wavelength of light, which was like this, right? What is the wavelength here? 2 feet. Now, the universe expanded, the wavelength also expanded, right? The wavelength expanded to something like 4 feet, right? Got it? Because the expansion, the wavelength of light also got stretched, because of which the energy decreases, and this is the observed redshift. Is it? Got it? Yeah.
Is energy not conserved?
It is not.
So where does that energy go?
So, as a child, I used to think that this is where dark energy comes from. But again, pipe dream, no, it does not. This energy is basically gone forever. It's lost to the expansion of space. So, yes, you have heard energy is not created or destroyed. Wrong. On universal scales, energy is destroyed, energy is created. Out of nothing.
Can
And
we
goes
say
into
that
nothing.
this
Yes.
energy is being used to expand the universe?
As I said, I thought so too, but no. The expansion of the universe is not coming from this energy. It's coming from some other energy. So basically people have tried, people have thought about it. But this energy is not enough to explain the observed expansion of the universe. So there must be some other energy.
And if
Yeah.
the waves are expanding, then why the matter is not expanding like that?
Huh?
Why matter is not expanding like that?
Matter is expanding, some sort, because galaxies are moving away from each other. So matter is moving away from each other. It is expanding.
No, like
Now,
a matter particle. Why is it not expanding with space?
so what is happening is, what keeps matter together? electrostatic force, gravitational force, strong nuclear force, right? So these forces are simply winning over this expansion.
No, not that expansion. Like
Then?
if we see fundamentally, the light waves are expanding, like they
Yes.
are stretching. So why are not matter particles like neutrons, protons, electrons?
Because it's a particle and it's bound by this force. That is the whole point. So if you have an atom, which is, let's say here, you have this nucleus and you have this electron cloud, whatever, right? This is bound by electrostatic force. This electrostatic force basically prevents this atom from expanding,
So the universe,
even if the space between them is expanding.
the space is forcing it to expand, but the forces are like constraining.
Exactly. So when you have these small scales, the expansion is not a lot. Okay. As I said, the expansion rate is the Hubble constant, 60 kilometers per megaparsec in 1 second. Okay. A kilometer is much smaller than a megaparsec. So at these small scales of, let's say, whatever, 1 nanometer, 1 angstrom, the expansion of space is very small. It's almost negligible.
So,
And at
but
those
there is,
scales, electrostatic force wins.
so the particles are expanding, but the expansion is negligible.
No, as I said, even if the space expands, electrostatic force will keep it at the same distance. Okay? Because as you remember, stable orbits exist at stable distances. Right? Right. And this redshift, now that you understand a little bit more, comes from this expansion of space. And this expansion of space is actually determined by this factor known as A, the scale factor. Okay? Again, a very important term in cosmology, the scale factor. And that is how we actually parameterize the expanding universe. How do we do that? For that, we go into a little bit of mathematics. Please bear. You have a metric in a flared spacetime. So, how do you measure distances anywhere? How do you measure distance between 2 points in R3 coordinates? You have dx squared plus dy squared plus dz squared. Right? Now, if I go into a flat spacetime, if I also include 2 events that are happening at different times and at different locations, how do you calculate the distance between them? This formula. Okay? And this minus c squared terms and these plus terms here represents the metric. Okay? Whatever the sign is, that comes from something known as the metric of this spacetime. Okay? Now, if I want to expand the spacetime, what will I do? I will add this expansion term. So, time is unaffected, but the space coordinates are changing with time. Got it? This expansion is basically completely summarized in this single term, expansion term. And how it is actually parameterized? We assume that at present, so that is A naught, the present scale factor is 1. Okay? So if I am looking at time before, A minus, will it be less than 1 or greater than 1? But the distance is smaller in past, or were they larger? Smaller, right? So that means A must have been smaller than 1. Okay? And then if we go to much long ago, minus, I don't know what I'm doing, but yeah, so this must be much smaller than 1. Right? What that means? The universe was smaller. Right? If in the future it is expanding, in the past it must have been smaller. It must have gone down. So this is actually the birthplace of the Big Bang theory or the Big Bang model. If the universe is expanding, that means in the past it was smaller, all the things were closer together, and at some point everything existed at the same point. Right? So this is the universe today, just an analogy. This was at some time before, and this was again in more past, and then at the start of the time, it must have been a single point. Okay, the whole universe came from a single point, which must, because things were closer, it must have been hotter and much higher energies and much higher densities. Any questions?
The time is finite now, like
Yes.
till now, which has passed. So
Yes.
we, on the basis of just this, how can we say that it was at the same point?
So basically, if you track again, just look at this video, right? If you have these two galaxies going apart, what would happen if you go to the earliest time possible? They begin very close, right? But if you, unless you have any problem, you can go further back in time. They would have been even closer. They would have been so close that they would have actually overlapped, right? Does that explain it?
No, I was asking that suppose the age of universe is T naught.
Yes.
So suppose it's starting from some like from the origin of universe, and T naught time passes.
Yes.
Then the like that bubble would have expanded to the present day bubble. Right?
Yes.
So how on the basis of this we can say that that initial bubble was a point, not a space.
Okay. So again, the T naught time, where does it actually come from?
Actually, what I had read about that Hubble constant, that 1
Yeah.
by h naught, because the graphs when you plot it, it meets at the origin. So that must be the point when all of the matter, everything was at the same point.
No, at least not in this Hubble diagram. The one I showed you, you had a straight logarithmic graph, right? No, that meeting to zero actually does not mean that all the points should have been in the same space. That simply represents a smaller distance, so the things nearby us. That actually does not have anything to do with time. Okay, it does not even actually take into account the expansion. So T naught that you said, the age of the universe, it is defined in that terms that if the universe started from a point, it would have taken T naught time to expand the current space. The age of the universe comes with the assumption that it started at a point. Does that explain? You cannot actually think of any other way where the universe was some initial size like this, right? And there it t equals to 0 happened. How do you basically how do you theoretically explain t equals to 0? When did time start? This gives you a much simpler answer when everything was at the same point. Okay? Okay. Any other questions? The space is expanding. Is the space inside your brains expanding, or are you understanding this? Okay, good. I don't know what I said. Sorry about that. Yeah, so as I was saying, expansion of the universe determined with this scale factor A. Okay. Now we move on to another very interesting fact, that is, how do you use a telescope as a time machine? Any idea what I am talking about? What? You guys are nodding your head. Tell me answers. Speak. Exactly. Light takes time to travel, so there must have been some finite time between the light being emitted and us seeing that light. Always. What it means, you all know what is a light year? What is a light year? Distance traveled by light in a year. Right? So, if you look at the sun is 8 light minutes away. What does that mean? That the sunlight that is observed on Earth was emitted 8 minutes ago. Got it? If the sun disappeared instantaneously, or let's say turned into a black hole, we would not even know till 80 minutes that the sun has disappeared. Okay? Even if you push the sun out of the solar system, okay, some random event happened, some primordial black hole came, it threw the sun out of the solar system. Even the sun, Earth's gravity, the solar gravity, which is keeping the Earth in the circular orbit, even that will not know that the sun has disappeared, because even gravity travels at the speed of light. So Earth will be bound to this same orbit for 8 extra minutes, even if after the sun has gone. Yes.
How do we know that gravity travels at speed of light?
That comes from general theory of relativity and basically the assumption that nothing travels faster than speed of light. And this has actually already been observed in something known as gravitational waves. Right? Heard about gravitational waves? Very interesting stuff, you should read about it. These are waves in the space-time, which is basically gravity traveling. And these gravitational waves travel at the speed of light. Okay? Theoretically and even, have they been observed? Have you measured the speed of gravitational waves? Vibeshan?
Yes.
Okay, yes. So we have measured the speed of gravitational waves. It is the speed of light. Got it? Yes.
So not be true with homogeneity and isotropy of God.
Where?
This 8 minutes and 1, 3, 4, 4 years of not be true. Homogeneity and isotropy of God, because light would take different times to go and
Yes. So if you break homogeneity, he's saying if you break isotropy, then light would have different speeds in different directions. Okay, so that's why also you should keep isotropy. Then you could basically this will not remain. Yes.
But this is a small scale, so how do we know that homogeneity holds for like 1 astronomical unit or something?
So honestly, homogeneity, again, what does homogeneity mean in terms of what do we say? Laws, physical laws that we have, we assume that they are homogeneous at infinitesimal distances. So at all distances. Okay? How do we know that? People have done experiments. You have satellites which are near the sun and which are theoretically completely understood. Right? Their orbits are completely understood. So the gravity works at the same way at these distances. And we assume, unless you go to something like modified gravity or modified Newtonian dynamics, there they say that gravity works differently at different scales. That actually breaks a little bit of homogeneity. Okay, so we'll not go into that. As I said, cosmology, most of cosmology assumes isotropy and homogeneity. That's why it's an assumption. You can't always prove it. Right? So, Orion's Nebula, 1344 light years away. So we are observing light which was emitted 1344 years ago. Similarly, looking at the Andromeda Galaxy, 2 million light years away. So we are looking at light which is 2 million years old. Okay? So I like another joke that I like to make is, if there are aliens in Andromeda, they cannot look at us. They would actually be looking at early humans that were alive 2 million years ago. Okay? They can't actually look at us, we can't actually look at them. Good. Another simulation that I have, let's again see if I can run it. Okay, yeah. So this is a look back time. So you can adjust how far you are away from the star. Let's say, give me a distance, 2000 light years. Okay, and let's say the supernova occurred in 28 AD, right? You all know BC and AD, before Christ and Anno Domini. So 2000 years ago, the blast happened at 28 AD. And now, if I let the supernova go boom, you can see the light from the supernova, the circle, it is moving away, and finally it has reached us after 2000 years. And when did we observe the supernova? So the supernova was 2000 light years away, happened in 28 AD. When will we observe the supernova happening? In the year? Say it loudly. 2028. Simple enough. Right? You can play around with it. Again, it's a very simple simulation. You just move around the person, the observer, changing the distance between the supernova and the observer, and you can see when the light reaches us also changes. Right? Simple enough. Okay. Coming back to the presentation. Yeah. So as I was saying, looking far is looking back in time. Whenever you look at an object which is x distance away, you are looking at it c by t times in the c by x time before, right? Yeah, I said that. Okay, so another beautiful video. Let's see if the sound is on. Okay, there is no sound. There is only sound in the laptop. That's fine. So these are images from the Hubble Space Telescope. What it did was, it looked at a patch of sky where you could not see any stars, right? And it kept looking at it for almost a month. And what did we observe? In this small patch where you see very less number of stars, you would think this was almost empty. You would think there are no galaxies, there is nothing to be observed in this area. But this is the image that was actually observed. This is called the Hubble Ultra Deep Field. That is, you are looking at the same place for such a long time, and this is a very small area. Yeah, this is a very small area of the sky. Okay, like much smaller than the size of the moon. And in that, you see all of these different objects. What are these objects? Every single one of these points is a galaxy. Can you count how many are there? No, it's difficult. There are over thousands of galaxies. I think almost 10,000 galaxies are there in this single image. And this actually increased our estimate of galaxies in the universe. First, we used to think there were around 1 billion galaxies in the universe. Now we think there are more galaxies in the universe than there are stars in the Milky Way. So 3 to 4 trillion galaxies in the observable universe. Okay. And all of these galaxies are spread over a large redshift. Yeah. So this is what we were observing, but it also extends in redshift. So in time or in distance, some of these galaxies are much farther, right? The distance to them is much more. The redshift is much higher. So this is what it actually should look like. And you see, number of galaxies near us are less, and as you go farther and farther, the number of galaxies increase. So we are observing all of these galaxies at these high redshifts, right? What does that mean? We are looking at all of these galaxies at very early times. These galaxies are 12 to 13 light years away, 12 to 13 billion light years away. Okay, very far. So we are looking at them as they were 12 to 13 years ago, which is almost the start of the universe. Do you know the age of the universe? What is the estimated age of the universe?
14 point something.
14 or 13.6 billion years. And what we are observing? Galaxies up to 12 to 13 billion years old, right? And this also allows us to study how these galaxies form. So when you look at galaxies which are very nearby, you see these kinds of grand spiral galaxies, and they are much larger in size, much larger in mass. And when you look farther and farther away, you start seeing smaller, deformed or early formed galaxies. So this is how you see that galaxies form. Small galaxies formed, these merged and formed these larger galaxies that we see today. Okay? right? So this is how telescopes are your time machine. You are looking away, you are looking farther away in distance, but you are also looking back in time. Now what this gives you, as I said, we have a finite age of the universe, 13.6 billion years or 14 billion years. That would mean there is also an edge of the universe, right? If an object is farther away from 13.6 billion light years, it's more, let's say 18 billion light years, okay? That's wrong actually. If it is, let's say 18 billion light years away from us, light from that has not had enough time to reach us, right? Because the universe is not old enough for light to come to us, right? What that means, you can also understand it in a very different way, is that we had the Hubble law, Vr equals to h naught d. The speed of a galaxy moving away from us is dependent on the distance. So if we look at large enough distances, these galaxies would be moving at the speed of light, right? Distance can go as long as you want. Is it true or not? What do you think?
How can they move at speed of light?
They are, as I said, they are not actually moving at the speed of light. What is happening?
Space.
The universe is expanding. The space is expanding. But it seems, it appears as though these galaxies are moving at the speed of light. Right?
But relative to us, they are moving.
Exactly.
So, how can it be possible?
So whenever you say that nothing can move faster than the speed of light, you always add a few extra terms, which is the fine print. In the local universe, in a flat geometry, things like that. So basically, and you also add that information cannot travel faster than the speed of light. What is the information here? It's light.
Light.
Okay? And again, galaxies are not moving in actuality. What is happening? They are only appearing to move. As I said, the scale itself is getting longer. Space itself is getting bigger. The galaxies are stationary at their places. Got it? So it does not violate relativity. So yes, if you follow Hubble's law, there will be galaxies which are moving even faster than the speed of light away from us. What that means, that light from those galaxies will never reach us. Okay? So that is actually represented by this yellow orange line. All the galaxies which are beyond this line, this is called the Hubble sphere. Okay? All the galaxies beyond this line, which are farther away from this, are moving at speeds greater than the speed of light. Okay? And the light they are emitting today, okay, in the present time, they will never be, that light will never reach us. Okay? But then how have we observed these galaxies? They emitted this light at earlier times. So we have observed galaxies much farther away also. But all of these galaxies were closer to us at earlier times. Okay? So at earlier times, when they emitted light, they were closer to us, and so light has had enough time to reach us. But now space has expanded. Today they are moving at speeds faster than speed of light.
So, the galaxies you showed recently, the bunch of galaxies, so it is possible that some of these galaxies are right now moving at more than speed of light.
So every white point in this sphere is actually a galaxy. I forgot to mention. It's actually a galaxy cluster. So this has all the trillions of galaxies that we have. All of them are here inside this observable universe. So the earlier one, which I showed you, HDSS data, that actually contained very little galaxies in this nearby region. Okay? So what I am saying, we have observed galaxies outside this Hubble sphere, but the light that they are emitting at the present time will never be able to reach us because they are moving faster than the speed of light. Okay? But then, so this is the yellow circle. How do you define this last limit? That is, if you keep looking far, you will keep looking back in time, and eventually you will look at the time when the universe was a point. right? And you cannot look further. So that is your edge of the universe. So this is the formula for Hubble sphere, the radius for Hubble sphere, which is around 4.1 billion parsecs. Okay? Then see here, 1, 2, 3, 4, 4.1 billion of gigaparsecs. That is the Hubble sphere. The observable universe is much larger, 14.3 billion parsecs. These galaxies can be observed today, but in the future, they will not be able to observe. We will not be able to observe all of these galaxies as time goes on and on. Okay? Okay.
So
Good.
by this, can we like estimate where is the center of universe, like the site of Big Bang?
Again, when there is no center of the universe.
But there's a site where all the sphere will.
Yeah, so this will be the center of the observable universe. Important question. Are there galaxies outside this observable universe? Yes or no?
Yes.
Yes. Okay. There are many more galaxies outside this observable universe, but we cannot observe them. We cannot, light from those galaxies will never ever reach us. Okay? Now, this observable sphere will shift depending on where you are. We are here at the center. We are in the Virgo supercluster. Okay? Now, imagine we were here. The observable universe shifts. It's a circle or sphere around you here. Okay? Then Virgo supercluster would be a part of your observable universe, but you will be able to see galaxies here. Right? So you see, the center of each observable universe is basically the observer. That is the whole point. The observable universe is defined with respect to our observer. And if you agree with homogeneity, every observer should have an observable universe, so the universe should actually be infinite. How did we make that jump? How is the universe infinite? Just from the fact that every observer should have an observable universe. Yes. Exactly. So if you have an observer here, that will also have an observable universe. Now, at the edge of that observer's observable universe, also will have its own observable sphere, and so it goes on and on. You can actually never think of an end. So there is no real edge to the universe. There is no end to the universe. That is what I believe. Okay, it's a philosophy. Again, it's not proven. This is what I believe. This is my belief system that the universe should be infinite. Some people do believe that the universe is finite, but yeah, we'll not go too deeply into that. Yes?
In finite time, shouldn't Big Bang expand to a finite volume?
Yes, not true. As I said, this expansion can happen at speeds greater than speed of light, right? So this distance, as I said, is increasing faster than the speed of light. So the universe can expand faster than the speed of light.
Even if it's faster than speed of light, it won't be infinity. So if
What?
It won't be infinite, na? So if there's a
Okay,
specific
but that is what I'm trying to say. If the velocity increases with distance, you could have infinite velocities, relative velocities.
do we know the rate of expansion of the space?
Yes, we do.
So by that can we calculate like from the beginning of the universe till where it can expand at the most?
Not exactly.
Why?
We still are not clear how the universe expanded at very early stages. We know how the universe is expanding today, but that expansion, that scale factor I showed you, A, actually changed with time.
So we don't know the whole function.
We don't know the whole thing very accurately. Let's put it in one way there. And also, it is quite difficult to honestly answer how these things would happen. But yes, it's not necessary that there will be a finite distance that things would have traveled. Because that also puts you into another type of questions. What is the universe expanding into? Right? There must have been space around the universe where that universe is expanding. Only then you will have an edge. Right? I subscribe to the philosophy that there is nothing beyond the universe, because the universe is all there is. So space exists only inside the universe, so you do not have an edge or a bound. Okay? Again, you can have a different idea, you can have a different philosophy. You are open to read about it more and form your own thoughts. Okay?
You can have infinite space, we are infinite space, hence the matter was created at the Big Bang.
Yes.
You can just take that the space started expanding at the Big Bang.
Yes,
The
possible.
matter expanded along with the space. So there is a hard limit to how far the matter will reach. But the space
True.
itself is infinite.
Space
True.
and time we define for the universe itself, right?
Sorry,
Not
can you
beyond
repeat?
it. Like space and time, the concepts we have defined just for universe.
Exactly. So as she says, the concept of space and time is defined for the universe, but again, some people can extend it to beyond it as well, right? That is what he is trying to say. If you can have space beyond the universe as well. What is stopping? Some people believe, like me, that space and time itself began at the Big Bang. So there was no concept of time, no concept of space before Big Bang. Yeah.
Then if we consider space to be infinite, and then there is something some limit to the expansion or something like that, then how do we define homogeneity? Because homogeneity we are defining in space, right? So
Good.
it should encompass the complete space.
Very good. So, as she points out, if you want to assume homogeneity, you cannot have an edge of the universe, right? Because when you are near the edge, the universe looks different in different directions because you are at the edge, right? So, if you assume isotropy and homogeneity, that basically gives you an infinite universe, as I said before, observable universe around different points, right? That's where homogeneity comes in. You can assume homogeneity breaks, and then you can have an edge of the universe. Got it? You could actually have edges even in a homogeneous universe. I'll come to that later in the slides, the last topic for today, where you have a finite universe, but you still have something edge. Okay, it's not an edge, but yes, the universe is finite. It's not infinite. It still does not have an edge, and it's still homogeneous, it's still isotropic. Okay, good. Next, we move on to, what is the time? Quite late. Okay, so this will be the last topic, the shape of the universe. We all have studied the angle sum property of the triangle, right?
Yes.
What does it say? Sum of the internal angles of a triangle is 180 degrees or pi degree, right? This is your triangle, you sum the internal angles, always 180. The problem here is, this is only defined in a flat space, okay? If you have curved space, like a sphere, you could actually have a triangle where all the angles are 90 degrees. How is that possible? Stand at the North Pole, then move to the equator, move along the equator, go back to the North Pole. The angles you made were all 90 degrees, but you drew a triangle, right? So this is a positive curvature. This is a sphere, okay? The opposite is also for a negative curvature surface. So this is like a saddle. One side it is curving convex, other side it is curving concave. This is a negative curvature, okay? Here you can have the sum of the angles less than 180, okay? Triangles are, if you try to sum them up, they will come out to be less than 180 degrees, okay? Now, the theory that we have, that the universe should be homogeneous, isotropic, it should be expanding. That can be done in all three of these curvatures. That can be equally well explained in all three of these systems, right? So we must make observations and try to find out which is true. Does the universe have positive curvature, negative curvature, or flat curvature? But what does it actually mean? What does this curvature actually tell you? So it is similar. Have you heard about curvature of space-time due to mass? So gravity in general theory of relativity is equated to curvature of space-time. if you have a mass, let's say sun, the space-time itself curves around that sun, and that causes a force of attraction. Okay, that is gravity. Similar to that, the whole space-time of the universe can also have a overall curvature. Got it? And that will depend on all of the mass inside the universe. Right? Okay. Now, how can you actually observe the curvature of the space-time? You have two parallel lines. Let's say we are an alien who has these very powerful laser lights, and we throw as two parallel lines. Okay? In a flat universe, these two parallel lines will
Never ends.
stay parallel. They will never meet. In a positive curvature universe, they will first diverge and then they will converge back. Okay? At some very high distance, at some very large distance, but these parallel lines, they will meet. Why? Because the universe itself is curved. Okay? Yes.
But on a sphere,
Yes.
two parallel lines wouldn't mean two parallel planes intersecting the sphere.
So it's different from a parallel plane. So when you talk about light takes something known as a geodesy along a curved space.